Welcome to the 7.4 notes. We are going to be talking about how to graph rational functions. At the top right of the page, you will see an example of what graphing a rational function might look like. Before we jump into how to find all of it, I'm going to give you kind of the 5 main pieces that are on a rational graph. The first one is you might see that there's like a little open circle right here. That is called a hole. It is left behind when common factors are canceled out. It's an x value that no longer works with the problem, but is still kind of part of the graph, so we draw an open circle instead. Then, any line dashed like this that's going up and down in the middle of the graph is called the vertical asymptote. And we're just going to call it the VA for a minute, but it's also listed in step 3 over here, vertical asymptote. An asymptote is a line that the graph gets really close to but never crosses. So you'll notice that it's kind of going almost parallel to it at the top and the bottom, because it's not going to cross, but it is going to get really close. The same idea also happens going side to side. Since it is side to side, we call that the horizontal asymptote. Same idea, just going side to side. That will be the last thing that we usually find. So it's going to be our step 5. Then, anytime you have the graph cross the x-axis, which is the one going side to side, that is called an x-intercept. Or you might remember us calling it a 0 before. Anytime it crosses the y-axis is going to be the y-intercept. And sometimes we'll have to find other various points around the graph so that we can draw this curve, but those are the 5 main pieces. Holes, vertical asymptote, horizontal asymptote, the y-intercept, and the x-intercept. And we are just going to start one step at a time. The first thing you always want to do in any of these rational functions is factor first, so that you can find any common factors that are going to cancel out. Okay, so we are always going to start by factoring. And always try and factor the top and the bottom. Sometimes one of them won't work, and that's fine. So for example, on our first one down below, there is a 2 in front of the x squared on the top. So this is one where you're going to have to find two numbers that multiply to negative 2 and add to negative 1 in the middle, which is negative 2 plus 1. But since there's a number in front of x squared, we have to split the middle. Meaning, instead of negative 1x, negative 2x plus 1x. And then we keep the 2x squared and the negative 1 at the beginning and the end. So these two numbers are going right here and here. Then we split it down the middle. I can divide the first two terms by 2 and take away an x. Dividing by 2 gives me 1 and negative 1. And taking away an x leaves an x on the first one, and it gets rid of the x on the second one. Then I can't divide by anything on the other two, so what I do is I go ahead and put a 1 out there, but it's still going to be x minus 1. You'll notice that my two parentheses match. They are both x minus 1, so that's the first factor. The other factor is 2x plus 1. Then I also have to factor the denominator of a fraction, which does not have a number in front of x squared, so I just need the two numbers that multiply to negative 12 and add to negative 1, which is negative 4 and positive 3. Now, is there a factor that is on both the top and the bottom? No. Since there's no common factors that cancel out, there will be no holes. Because a hole is created by the zeros of factors that cancel out. And we didn't have any factors that cancel out, so we don't need to list any holes. Which takes me to step 3. So we didn't have any answers for step 2. Step 3 is the vertical asymptote. It is where we are going to set the denominator equal to 0. Because you can't divide by 0 in math. So x is not allowed to be any value that makes the denominator equal 0. So I'm going to come over here on the left and write VA for vertical asymptote, and I'm going to set both parts of the denominator equal to 0. Which means x equals 4 and x equals negative 3 are my vertical asymptotes. So on my graph, I'm going to draw a vertical line where x equals 4 and negative 3.
Now let's move on to step 4, which is the x-intercepts. And like I said earlier, the x-intercepts are also called the zeros because they are when the whole fraction equals 0. But it actually turns out that no matter what number you put on the bottom of a fraction, this whole fraction is going to equal 0 if you put a 0 on top. Because 0 divided by anything equals 0. So for x-intercepts, we only want to set the numerator equal to 0. So it solves just like the vertical asymptote, but top instead of the bottom. So for x-intercept, The top part is x minus 1 and 2x plus 1. For x minus 1 equals 0, you would add the 1 to the other side, and x would equal 1. So our first x-intercept is the point 1, 0. Because the y value, what this equals, is always 0. Then for the next one, I would subtract the 1 to the other side, which is going to give me 2x equals negative 1. And then I would go to divide by the 2, and it would be negative 1/2. So my other x-intercept is negative 1/2, 0. There are not always two. Sometimes there are, sometimes there aren't. We're going to go ahead and put those 2 points on the x-axis at 1 and negative 1/2. For the y-intercept, the y-intercept is when x equals 0. So really, we're going to plug in 0 equals x for the whole equation. Sometimes this will be more complicated than other times. I'm going to go ahead and make some space over here on the right side for the y-intercept. It doesn't need a lot of space though, because we are going to plug it into the original equation. Now, there is a reason why I suggest plugging it into the original equation, and I'm going to go ahead and write original equation above y-intercept, because when it's not factored and it's multiplied out, 0 squared is just 0. Minus 0 is still 0, so we get negative 1 on the top. And on the bottom, 0 squared is 0, minus 0 is still 0, so it's just negative 12 on the bottom. So our y-intercept is 0, 1/12. Now it is important to note that because it was negative 1 divided by negative 12, those negatives cancel and make it positive 1/12, which is going to go right here. You do need to know that it is slightly on the positive side of the y-axis. And then lastly, we have to find our horizontal asymptotes. There are 3 rules that you are going to use to find these, and it is based on the degree of the numerator and the degree of the denominator. Basically, whichever one has a higher exponent. So in this case, we have an x squared on top and an x squared on the bottom, so they are the same. If the degrees are equal, your y, or your horizontal asymptote, is always at y equals the number that is the leading coefficients divided by each other. So in this case, the horizontal asymptote is y equals, and I'm going to go ahead and circle it for you, 2 over 1. It'll always be the numbers in front. That is why they are called the leading coefficients. So there's a lot of work going on here. This part right here is the factored version of the problem. You set the denominators equal to 0 to find the vertical asymptotes. You set the top equal to 0 to find the x-intercepts. And you plug in the number 0 for x to find the y-intercept. Then you have to follow the rules for the horizontal asymptote. If the degrees were not the same, if the numerator has a lower degree, like x over x squared, then it would be y equals 0. If the numerator has a higher degree, then there is no horizontal asymptote. it has what is called a slant asymptote. We're not going to see any of these. Those are reserved for college algebra. You will relearn all of these rules again in college algebra, but it's going to be pretty important that you already know these because it gets a little bit harder with the slant asymptotes, which is what happens in that third example of the horizontal one. Okay, so our horizontal asymptote was at y equals 2, so we need to draw a horizontal line up 2. And that kind of guides my line here in the middle, like this. Then I need to find 2 extra points on either side so that I can, because there are so many other parts, I'm just going to give you the pattern that is, it would then be up here and up here. Since that bottom part was in the middle, then on the other 2 sides, it's going to be in the top left and the top right, and it's going to follow close to this asymptote and then close to this asymptote. Close to this one, and close to this one. I will explain how I find that out on the next 2 a little bit better, because this one already has so many parts. I want to go over domain and range before we get too far into the rest of it. So for domain and range, I just need you to tell me domain is x values. So in this case, x cannot equal 1 or -1, In this case, x cannot equal 4 or -3. That's where we put our vertical asymptotes. For the range, y cannot equal 2. So the asymptotes become the values that the domain is not equal to. The whole would also be a value that x can't be, except we don't have one on this example, so we don't have to worry about that too much. All right, once you have that one written down, go ahead and continue on to the next one. Not all of them have that many pieces to them. The factoring was just a little complicated on that one. Okay, the next one's a lot easier because they are both trinomials with no number in front or with a 1 in front. So the 2 numbers that multiply to -28 and add to 3 are 7 and -4. So our factors are x plus 7, x minus 4. And on the denominator, we need 2 numbers that multiply to 35 and add to 12. So our factors are going to be x plus 7 and x plus 5. 7 times 5 is 35. 7 plus 5 is 12. I do have a factor that I can cross out this time, which is the x plus 7s. So I can cross that out, but my whole is going to be wherever x plus 7 equals 0. If you solve that equation, you would get x equals -7. So -7 is the x part. We need the y part of the point too. And whenever you have the x part of a point and you need the y part, you simply plug the x in. The only thing is you can only plug it into the equation that remains. So this one right here, x minus 4 over x plus 5. Which would be -7 minus 4 over -7 plus 5. -7 minus 4 is -11, and -7 plus 5 is -2. And if you divide -11 by -2 in a calculator, you are going to get 5.5. So 5.5 is the y value of the whole. Almost always you're going to see fractions in each graph somewhere because they're fractions to start with. So it would take a lot of luck to get an example in which nothing ends up being a fraction. What that means is the point -7 5.5. So left 7, up 1, 2, 3, 4, 5.5, which is like right there, is going to be a hole though. So instead of drawing a point, I need to draw an open circle like this. Now it acts just like a point on the graph, but instead of being an actual closed circle point, it's a hole where we have found an x value that wouldn't work in the original problem before we crossed off the x plus 7s. So it only happens if you end up changing the equation by crossing something out. Then I'm going to go through the steps that I had done before, but a little bit faster this time so that maybe it sinks in a little bit more. For the vertical asymptote, you set the denominator equal to 0. And the only thing left on the denominator this time is x plus 5, because I crossed out the x plus 7. So if x plus 5 equals 0, then x has to be negative 5, because you would subtract 5 from both sides. So my x-intercept is the point negative 5, 0. Right there. Then so my vertical asymptote is x equals negative 5. Then I'm going to go find my x-intercept. My x-intercept is when the whole fraction equals 0, and that only happens if the top part equals 0. So this time you are setting your numerator equal to 0, which is x minus 4. And if I add that 4 to the other side, x equals 4 is going to be my x-intercept. So the point 4, 0. The next item on my list is the y-intercept. For your y-intercept, you're always plugging in 0 for x. So 0 squared plus 3 times 0 minus 28 over 0 squared plus 12 times 0 plus 35. And the whole idea behind the y-intercept is all of these zeros just make 0. So really I just need to do negative 28 divided by 35 in a calculator, which is actually negative 4/5 or negative 0.8. So my y-intercept would be the point 0, negative 0.8. As I go to graph this, I'm going to realize that negative 0.8 is pretty close to negative 1. So on the y-axis, I'm going to go down almost 1 and put my point right there. Then for my horizontal asymptote, that's where I have to check the degree. It is the same like it was on the last problem. And when it is the same, your horizontal asymptote is the two numbers out front divided. Which there are no numbers, so it's just 1 divided by 1. So y equals 1. Which means you're going to draw a horizontal line up 1. And I have a point in this corner and this corner, which means that those are going to be the two corners I use, kind of like the example on the top right. How the curves were in opposite corners. It's going to be just like that, except I go through these 2 points, and when I go towards the left, I'm going to curve it as close to the line as I can. Then on the left side, I only have that one point to go through. It's actually the hole. So I'm going to start there and go as close to the vertical asymptote and then curve it as close to the horizontal one as I can. Just like that. This time for my domain, my vertical asymptote was -5. So x can't equal -5 or -7. That's where the hole was. For my range, the horizontal asymptote was 1. So y cannot equal 1. Sorry, I forgot to put the slash through that on the x's. And y cannot equal 5.5. That part comes from the hole. So the hole gives you an x value that can't be equal to on the domain and a y value for the range that can't equal. All right, this is going to be our last one that we graph, and then I'm going to kind of talk about pulling all the pieces together for the last one. On the next problem, the top part can't be factored because it's just x plus 5, but the bottom part can factor into x plus 4, x plus 5, since 5 times 4 is 20, and 5 and 4 add to 9 in the middle. Then you'll notice that my x plus 5s actually can cancel. As I cancel those out, I need to write over here on the side that I have a hole where x plus 5 equals 0. The reason why we have to set it equal to 0 is because that would have been a vertical asymptote before, because you can't let the denominator equal 0. But now that we're taking it away, it leaves this hole behind. That means that x would equal -5. And I have to take that -5 and plug it into the equation to find out the y value for the hole. Before I do that, I'm going to go ahead and write this fraction over here. X plus 4 is the only thing I have left on the bottom. And everything from the top canceled, but we can't just leave the numerator blank, so we need to leave behind a 1. Not a 0, because 0 divided by anything is just 0. That kind of cancels anything out. So I need to plug that -5 into this fraction that's left. And -5 plus 4 is -1. So 1 divided by -1 is -1. So the point -5, -1 is my hole. Then I'm going to go through the same steps I did on all of the others. Vertical asymptote. Set the denominator equal to 0. The denominator is x plus 4. Then you would subtract that 4 to the other side. So x equals -4 is my vertical asymptote. And I'm going to draw a dashed vertical line to the left 4, because that's where x is -4. Then I'm going to find my x-intercept by setting the numerator equal to 0. Because if the top part equals 0, the whole fraction equals 0. But the top part of this fraction is the number 1. Does the number 1 ever equal 0? No, and I don't have an x left to solve for, so this means that there is no x-intercept. And I'm going to come back and talk about why there's no x-intercept, what causes that to happen when we get down to the horizontal asymptote. And then for my vertical, or so my y-intercept, that's when you plug in 0 for x into the original equation, or you can plug it into the new one on this one. Since there aren't factors, it's not too bad. And that's going to give me 5 over 20. And 5 divided by 20 is 0.25. So my y-intercept is going to be the point 0.25, about here. And lastly, my horizontal asymptote is where I'm comparing the power on the top with the power on the bottom. The power on the top is only 1, so it is smaller. If the numerator has a smaller or a lower degree, then your horizontal asymptote is always y equals 0 for the horizontal asymptote. Okay, that is rule B, right, or rule number A, right here at the top. The numerator has a lower degree, so it's y equals 0. We just hadn't used that rule yet. Okay, so that means we need to draw a horizontal line where y equals 0. And you'll notice that that's actually the x-axis. And the reason why there can't be an x-intercept is because that's where the asymptote is. You can't have an x-intercept if it's where the asymptote goes. So anytime you get no x-intercept, it's because it's an example where y equals 0 is the horizontal asymptote. So I'm going to write that these two go together. No x-intercept means that it's y equals 0 for the horizontal asymptote. Then I don't have any other point than, or I guess I do have another point other than just the hole, but it's kind of hard for me to tell what's going on the right side of this graph. So I'm just going to add that at any point you can pick a number next to the horizontal asymptote, like -3, for example, and plug it into the formula. That would be 1 over -3 plus 4, which is 1 divided by 1. So the point -3, 1 is also on my graph, and that gives you an extra point to draw your curve through. I don't really need it on the other side though, because I have this point right here in the middle, so it's going to kind of go like that. For my domain, my vertical asymptote was x equals -4, and the hole was at -5. So here at -4 and here at -5, I had 2 breaks in the x values. For the range, it was 0 for the horizontal asymptote and -1 for the hole. Holes and asymptotes are what cause domain and range to have to take a break. So that is going to be where you get the numbers that you are putting here and here, always. Not the x-intercepts and the y-intercepts, because those are just points, but everything that causes you to have to break up the graph, whether it's a dashed line or a hole in the middle of the graph. Okay, the last two are really here to just help us kind of pull everything together. The first one says write the factored form. Factored means you want the parentheses. Factors go in parentheses. Of a rational function with a vertical asymptote of x equals 5. If x equals 5, that means that the factor would have been x minus 5. Because you would have added 5 to the other side to solve for x. And vertical asymptotes come from the denominator. So the denominator of this fraction needs to have an x minus 5 on it. Then it says that there's a hole at x equals 1. If x equals 1 is the answer, the factor would have been x minus 1. And holes have to be on both the top and the bottom. So x minus 1 x minus 1. That's it, guys. The only thing is it's asking us to write a function, so we need to write f of x in front, like this. The last one asks us for the standard form. That's the one that's like x squared plus x plus a number or something like that. And the only information that it gives us is that it has a horizontal asymptote of y equals 4. If the horizontal asymptote isn't 0, it's because the powers are the same and because the 4 is the leading coefficients divided. So give me two numbers that divide to equal 4, like 8 divided by 2. Then you need to give them the same powers, so like x squared and x squared. And the rest of this entire problem is up to you. I'm going to put plus x minus 2 and minus 6. All of that part that I just wrote in black, though, you get to decide on your own. Just don't forget to put the f of x equals in front.